Welcome to another chapter or another lecture on molecules in motion. What we had begun in the last class, we could not finish. In fact, we had just begun and we had to end the discussion. And the discussion was on finding out the diffusion expression for diffusion coefficient of a perfect gas using the kinetic theory of gases. So, when you are talking about kinetic theory of gases, this was the equation, this was the question we had taken up, which we have not discussed in previously. Remember, the distribution of the graph of our interest is a window of area A. We are looking at the particles which is reaching the window after traveling a distance of one mean free path. That means after traveling a distance of lambda. That means this lambda is the distance traveled between since the last collision of the molecule. So, if you had a collision here, the next collision will be here on the window of interest, and if that has to happen, then the molecules have to travel a distance lambda. Okay? So, that is how the mean free path is defined. So, what we are looking into, we are trying to define the diffusion coefficient. For that, the rate of diffusion of a gas is considered. For that we have calculated the net flux of molecules that is passing through this window as a result of arriving from a distance of say lambda minus, that means from left side to right side, or from by traveling a distance lambda plus, that means from right side to left side. When the molecules are traveling from the left side to right side, then you see, if I project that into the distribution of number of molecules with distance, then you see the lambda minus correspond to a location where the number density of the molecules is higher compared to that at the region of the window, if I take that as 0, where lambda is equal to taken to be the origin. So, if this is the distance which is going to travel, when it is traveling from say minus lambda, that means left hand side to right hand side, that means it is moving from a higher concentration of the numbers to a lower concentration. Okay? And how was that number concentration taken? We have discussed that in the last class, but here again I am going to say, when I am looking at the molecules moving, I am looking at a specific window area A. I am seeing the net flux that is passing through that in a window of area A as a result of molecules traveling a distance of one mean free path from either direction. One mean free path means that the next, whatever collision they had previously, their next collision will happen on the window of interest. Okay? So, this is the distance it is going to travel between the collision. That means the next collision with the wall should happen at a distance lambda, and this is the distance which we are looking into. And if I want to find out the number density at the various locations, and what is the number density in this place, what is the number density at this place and this place, what we had taken the Taylor series, expansion of the Taylor series, which we said that the number density of the particles or molecules at this region, that means at lambda equal to at z equal to minus lambda, is going to be a position which is going to be a value which is equal to the number density at z equal to 0 plus or minus. Here what I have minus the slope of say the change in number density with the distance. The slope is decreasing. So, I have a slope which is decreasing. That means that I at any of this position, what do I find out? What is going to be the value of number density? It is going to be slope of this curve. That means change of number density with distance, which is actually z, into that location, because at each location you have to find out, you can get the number concentration of the pot particle. So what is going to be that? I say let that distance be lambda. So we can have a higher series, we truncate the whole series at only the first differential, and what I see, it is the number density at minus this point is the number density this minus the slope of that plot, which is already a minus, into the lambda, the distance it is traveled. Okay, and this is located doing we are doing it as 0, means z equal to is 0 at considering that as the condition. Now the number of impacts which is happening on the surface is the number of frequency of collision which is there on the wall, which is nothing but the number of ZW into the area of interest into delta time t. And if I want to find out what is going to be the flux of these collisions on the molecule on the surface of the wall, then I should divide this by A0 by AT, and then the total number which you have here, the total number of molecules which is going to be coming to this position will be what? Will be the total number of molecules contained in this volume element. What is the volume element? The molecules are moving with the mean relative speed of c bar and in delta time t. So c bar delta t is the distance, and this is the area A or A0. So A0 into c bar delta t is the volume element. This is what we have said taking, and this is the number density which you are talking about. So that has to be multiplied, and if I if you take the expression, previous expression, it is 1 by 4, and if you divide it by the area of interest with the time taken, that gives you the flux, and as the molecules are moving from left side to right side. So what do you get? You get an expression of 1 by 4 number density at minus lambda into the relative mean speed. So therefore there is also a flux of molecules which is moving from the right side to the left side. The average molecules making the journey have the originated from z equal to plus delta lambda, where so we have, if we want to find out the number density at say at this point, what will that be? It is gone, all of this is moved to this side. So I can say, remember this is of a lower concentration. Okay, movement it is what we are looking is from left hand side, right hand side to left hand side. I am looking at moving from this side to this side. Okay, so what I have according to the Taylor series, I have the molecules at the lambda z equal to lambda. This is the molecule at z equal to lambda. Number density will be the number density at z equal to 0 or where lambda equal to 0 into the slope of the number density with distance, this slope into the lambda which distance it's traveled. So we have now, you see, similarly you can generate a flux for that, and flux for that will be what? The flux for that will be 1 by 4 again. Here you have the say positive lambda, value of lambda is positive here, c bar. Again this will cancel off. I hope you understand this, because we have been talking this for quite some time now, how to find the flux. Flux is the total parameters, whatever molecules or atoms which are undergoing the transport process, divided by the area of interest into the time interval delta t. So this is the number of molecules which is undergoing impact with the wall. And impact with the wall, how many molecules are undergoing the impact with the wall? all the volume molecules which is contained in this volume element. What is this volume element? The molecules are moving with the mean speed relative mean speed of c bar and in delta time t. So, this is the distance into the area of interest. Whatever is contained in this volume element will be moving, and how many, what is in that volume element, what is the number density? That is going to be the number density at lambda minus minus lambda, and according to the number of impacts which we have, I have 1 by 4. So, I am reduced to having 1 by 4 n minus lambda c bar. Okay. The flux of molecules from right to left, now I have taken left to right, I have now take right to left. What should I have? This is the value of number density at lambda plus value, that means this position. Now, the flux of molecules from right to left arise from the supply of molecules on the right, that means this side will be having a negative sign. And so, if I want to find out that, because this is, if I take this movement as positive, this movement should be negative. This movement has to be positive because it is according to the from higher concentration to lower concentration, and here the movement is from the lower concentration of higher concentration. So, it is opposite. So, we have to take an indication that whenever we are talking about movement from right side to left side, we have supply of molecules from right side to left side at z equal to plus lambda. The values will be 1 by whatever you had for the minus lambda case. For this case, in the number density at minus lambda, that will be 1 by 4 into the relative mean speed, but you will have a minus sign. So, to find out what is the net flux at the window A, which is of our interest, what we need to know? We have to add the two flux which is moving from left side to right side, that means moving from higher concentration to lower concentration, plus the flux which is moving from lower concentration to higher concentration. What does this negative thing mean? Negative flux cannot be negative. It is meaning that it is moving on the opposite side. It cannot move from the lower concentration to higher concentration side. So, if I have to find out what is the flux, the net flux I have to take, I have taken, this is the flux value from left hand side to right hand side. The value at left hand side to right hand side was 1 by 4. C bar I can take common. Minus is coming from this one for the particles for the number density at lambda plus. Okay. So, this is the flux I get. This is the flux at when you are moving from right to left, and what is the flux which you have when you are moving to right left to right? This is the expression. Okay. Now, you minus this and plus this will get, all the things can be taken common, only the number densities at the lambda minus the number density at lambda plus. Now we substitute the values of number densities. If you see, the number densities was given to be something like this. Okay. So, substitute this for the position lambda equal to z equal to lambda plus and z equal to lambda minus. So, this is corresponding to lambda minus. So, it is number of density at x equal to z equal to 0 minus lambda into the slope of the number, the change of number density with distance, that is z, minus what you have, we have here the number density at x equal to z equal to 0 and the differential plot of number density with distance into lambda. So, if you see this, these will cancel off. What you are getting? You are getting, this is going to cancel off. You are getting twice of this. this is also minus, this is also minus. So, you get a minus sign, and twice of this, twice of the number density with distance, slope of that, twice of that into lambda into the relative mean speed, and overall you have 1 by 4 outside. So, 1 by 4 multiplied by 2 becomes 1 by 2. So, 1 by 2 with a negative sign, this is the flux along the J. Now, if you look at this equation more carefully, you will see that the flux of molecule is the expression is saying the flux of molecule is proportional to the first derivative of the concentration, okay, and that to a negative sign, and this is nothing but the Fick's law of diffusion, Fick's first law of diffusion. If you compare the Fick's first law of diffusion and the expression which we have derived just now, what do we have? This is the Fick's first law, and this is the expression of flux of molecules which we have derived. So, this is, both of them have negative sign. These are negative concentration gradient. This is the number density gradient for flow of matter or flux of matter. Then we can compare and see that the d can be equated to half relative mean speed into lambda. This is the expression we get from the kinetic theory. But what happens is, if you see the table, you will see that the value is 1 by 3 lambda into the mean speed, the mean relative speed c bar. So, how do we get that value? What is the reason why we get 1 by 2, not 1 by 3? Remember, all these calculations are very crude. These are only used to find out the magnitude of order of d, not exactly the precise value of d. What happens if you look at this diagram, if you have taken account of the molecules which are undergoing collision, and if you are trying to find out the flux, the aspect which we have not taken into account or neglected is if you see this, molecules may have begun a long distance, a journey very far away. Molecules may have begun its journey very close to the window. It may have a very long flight. So, if it is flying from here to here, but the collision is taking place close to the window. Okay, that means if this is lambda, but in spite of the fact that it is lambda, it is actually having a very long flight. Since the path is long, the molecules are likely to collide before they reach the window. If the path is too long, then there are possibilities, there are n number of possibilities that the particles will be moving a long distance. And if the particles are moving in long distance, it is not possible that they will reach the window without colliding. So, there are chances of colliding. So, what we are looking at, we are looking only at the particles which are supposed to be very close by and within the distance lambda. We have overlooked the fact that this molecule which we are looking into may have a very long flight, and it ought to have gone into the graveyard of the molecules that have collided, and because if you have collided and lost, that is, we do not consider those sort of particles. But to take effect of these accounts, which we have not done, we have not considered a molecule which may have gone through a long distance before coming to the collision point, which the collision distance from the wall may be small, but it is gone through a very long flight, but we have neglected that. We have only considered them to be reaching the flight, reaching the window with the distance which is covered may be probably 1 lambda, but actually it may have collided before and should have been ideally gone to not to be considered. So, for this effect to be taken into account, what we have seen, it has been seen that if you take a factor of 2 by 3 and multiply with the values which you have, then you get the realistic value which is supposed to be lower flux than what you get from the calculation. So, for the equation which you have for the d is 1 by 2 into the mean free path into the concentration relative speed, relative mean speed, but actually what you get if you multiply with this by 2 by 3, then 2 gets cancelled, you get 1 by 3 means relative mean speed into the mean free path. So, this is the value which is more appropriate, which is what is listed in the if you can see, I don't have it in this lecture, but if you see in the previous lecture, then you will see the expression for D is something like this, and that is because we have taken into account the long flight molecules which would otherwise which should have contributed, but actually should have been going to the should have been buried, because they probably undergo a collision before reaching the window. So, if I have a correction factor of 2 by 3 multiplied by the whatever flux we have generated, if you can do that, if you do that multiplication, it has been seen that you go closer to the value which you observe. So, this D value is here now D equal to 1 by 3, and that is the more acceptable value. Now, we have what we have done, we have derived the expression for diffusion coefficient based on the kinetic model and based on the condition that we are looking into number of particles moving through a volume element, where the volume element is actually considered as the window of whichever molecules reach the window of contained in the area or volume surrounded by, what do you say, what is the distance, is moving with the speed, say relative mean speed of c bar and in time delta t. So, c bar into delta t is the distance with the window between the window and area of the window. These multiplication of A into the distance c bar delta t is the volume element we are talking about locating the molecules. Molecules located in this volume element will collide with the surface of the window, and that is how we are looking into how the collisions are getting impacted, and from that impact of the collision we are calculating the various parameters. We have calculated the diffusion coefficient. Now let us consider the thermal conductivity coefficient. For considering the thermal conductivity coefficient, we have to remember that we are looking into the molecules which are propagating or getting transported, but each of them will carry some certain energy. So, according to equipartition theorem, what you have, the average energy which is going to be carried by the molecules is going to be epsilon kT, right? And I put a nu because depending on whether the molecule is diatomic atomic or monoatomic or complex molecule, the nu of that energy should be changing. So, according to partition theory, you have the average energy to be E equal to nu kT. Nu is the one which is, say you write down 3 by 2 kT, 5 by 2 kT. So, nu for a diatomic molecule and for monoatomic molecule will be different. So, we do not want to distinguish between what is the condition of the nu value, because it depends from it will be different for a monoatomic to a diatomic to a complex molecule. We will keep it as nu. Okay. For a monoatomic particle molecule, the nu will be 3 by 2, right. So, the molecules passing through an imaginary window A0, it transports the energy, the average energy which is going to be transported by those molecules is going to be number of molecules into the average energy carried by them. What is the average energy carried by them? E, that is equal to nu kT, where K is the Boltzmann constant and T is the temperature in Kelvin. Suppose what we are assuming, the number density is uniform. There is no distribution, no concentration or number density difference in the medium. Only change is in the medium is the temperature. Okay. So, when we are talking about the thermal, when we would want to derive the thermal conductivity coefficient, we have to assume that the number or the concentration of the particles is uniform throughout the medium. Only difference is the temperature. Okay. And all the molecules when passing through the window A will transport the total energy equivalent to what each of the molecules are carrying, average energy carried by each of the molecule into the total number of molecules, right. So, on the average the molecules arrive from, say, left hand side. Let us see what we have. We can have from left hand side and from right hand side. See, left hand side I am putting that as lambda minus, means you are having a location where the energy is higher. Energy will be always again flow from higher to lower. So, what we have? We have, sorry. So, what we have? We are having an average molecules arrive from the left after traveling a mean free path distance from their last collision in a hotter region, and therefore energy they are higher in energy. Understood? So, whichever particle which is coming from the left hand side and traveling a mean free path distance lambda, that is the time which they had last collided was anywhere, and the next collision would have been in the window of interest. So, that is going to be this distance going to be lambda, and I designate that as plus lambda. So, minus lambda. So, whenever the molecules are moving from left and traveling a mean free path distance from left to right, and that means it is moving from the higher energy to lower energy region. Molecules similarly will arrive from the right side, traveling a same mean free path distance from their last collision, but that will be from a cooler region, right. This will be much a cooler region. So, these molecules when they are traveling, they will be going, it is not possible for the molecules to move from the colder region to high energy region. So, this will be always having a negative sign, indicating that the flow is spontaneous in the reverse direction. So, number average of the impact which you have on the wall, it is going to be given by 1 by 4 n, capital N, into the mean relative speed. So, if I want to find out the flux of energy from left to right, the flux of energy from left to right, this is the left to right, arises from supply of molecules from the left side, and left side will be always at a higher energy. So, if I can see what is going to be the total number of flux of energy which is going to be associated on that impact, I have to see what is the total number of molecules present here, and each of the molecules is having an average energy of nu kT. So, if I have to multiply the total number of molecules which is present in this volume element into nu kT, and what is the total number of molecules which is present in the area of interest? They are the A is the area of window, C bar is the distance, the mean relative speed which they are traveling in delta time t. So, A0 into C bar into delta t is the total volume element. So, this is the total volume element, okay, and into the total number of molecules, this is the number density, and each of the molecules will have a energy E. Okay. So, this energy is now evaluated at lambda equal to x equal to minus lambda. I am taking a movement from a distance of lambda from the left hand side. So, from the left hand side, this is the total number of collision per unit area, gives you the flux. So, flux is 1 by 4, C the mean velocity relative speed, into the number density into the energy associated, average energy associated molecules at z equal to minus lambda. Now, if we want to find out the average energy which is getting transported, we had talked about the number of molecules which is getting transported. Now, what is the average energy which is getting transported? Average energy is which is transported is the energy here plus, if you have this energy associated at z equal to 0, and then you take the energy at this point, with any point here will be the slope of distance, which is the temperature difference between these two regions, that means dt by dx into the position at which it is happening. So, what is that? The total, the average energy transported will be at x equal to minus lambda. X equal to minus lambda is this position. Have a look at this. This will be nothing but it will be E at 0 t. Okay. What is E? What is E? E is nu kT. So, instead of writing E at 0, we have, because it does not make sense to have 0 temperature. So, what we have taken is, instead of writing like we have written here 0, instead of writing 0, what we have taken is the energy at T, that is nu kT minus the nu kT into lambda into the change in slope of the temperature versus distance. So, this is the change, how the change is taking place in temperature with distance into the location at which you are looking at the temperature, that is lambda, that into the nu k will be giving you the energy at any distance lambda, and that should be energy at T, that means nu kT minus this value, right. Similarly, the flux of energy from right to left can be also evaluated. Right is the one where you have molecules moving from a cooler region to a hotter region, which is actually not possible. So, we always get a negative sign. Okay. So, there will be a negative sign here. Okay. So, right to left will be always having a negative sign into the C bar number density into energy at a distance x z equal to lambda. The two opposing flux of energies are therefore, these are the two opposing flux which we have at flux of energy at lambda minus and at lambda plus. We can evaluate and then we get this value. We will talk about this a little further in the next class. We will begin with the flux of energy and take over the expression for the coefficient of viscosity. We will ultimately take coefficient of viscosity, but we will first talk about the thermal conductivity. Thank you so much.